Yeah, we'll do this quick stream. We got a bunch of things. We have this 3D simulation that O3 ChatGPT O3 Mini High did for us. It did quite an amazing job in terms of what it can do. Did all the code. So it's using Canon ES JavaScript library for the physics. Yeah, we have the orbit control, the standard 3GS library. We have this JSON file with all the elements, so you can select which block you would like, change the color for it. It's kind of all pretty basic, but it's just impressive that the AI was able to do all the coding for this. You can select your cylinder as well. The cylinder one has meant to have a radius and stuff like that, but it does work as it is. Those are the cylindrical. And make them yellow. Yeah, the user interface is not great, but yeah, obviously the bot can improve that. Yeah, there is an opacity, different opacity for the different blocks. Yeah, obviously did all the HTML code. There's an explanation. Why am I not able to? Yeah, there's a how it works an overview at the bottom of the page. And yeah, all the JavaScript code. So you're using orbit control Canon. .300 lines of code. You cannot, you can pen, zoom in and out. You cannot move the elements around. You can select them, which is cool, and you can turn them, rotate them left and right. So there's quite a lot to the simulation. Quite a lot. Yeah, they're being edited in the same place, and then they collide with one another. That's why they jumpy like that. And you cannot move them around as it is, which is a bit of a problem. I did all the CSS that we're not gonna go into. Yeah, primarily we'll focus on the JavaScript, and mainly so we wrote this brief for the developer, and it has an overview. Have GitHub Copilot going as well. Yeah, I don't think GitHub Copilot is actually working in this document. I think it's only working in code. I'm not sure if it's doing anything. Though we could have reviewed the code that way. No, GitHub Copilot doesn't have any suggestions. Yeah, eventually we'll make it available on the website as everything else we do. Let's see what else we've got. Yeah, so those briefs with ChatGPT working really well. Once you have a brief for your web application, for your code development, and you covered everything needed, then you just pop it into essentially any LLM that generates code, and it seemed to work pretty well. Yes, so that's all the code being generated after including the brief. We just start from the brief, it starts making the code. As described in the brief, we did have a few bugs that it was able to resolve as well. So, mainly to the libraries. But now we have that sorted. It's interesting that all three mini Hi said it cannot interpret images, but then went and did it anyway. Yeah, the big blocks, they just keep interfering with one another. So well, next step for this would be rewriting the brief, the standalone document for the developer. It actually made the suggestions itself. In the brief, there's some things that are optional that yeah, it decided to ignore, which is fine. So I'm actually not sure if you give it a lot of optional things to do. I think it's actually, I suspect it might actually be a good way to go about it, because you don't want to restrict the robot too much. But yeah, we might get back to this one at some later stage. And made a few simulations as well. be up and running. Why I cannot hear it? That was again O3, ChatGPT O3. Each ball has different frequency, it was able to do that. And you have gravity and everything working, which is pretty impressive. Well, I was impressed. So you have low gravity and they're floating around. And simulate what's the noise in your brain. That way, and how many balls you have up in the air every given time. Yeah, it does that annoying sound thing. But yeah, that was to make an acknowledgement to ChatGPT O3 Mini High. Such a convoluted name, but yeah, I understand what they are trying to say by yeah, and it's there was one problem where it was re-rendering the whole thing. Like when you change the number of balls, it will respawn all the balls, as opposed to now it will actually add and remove. So when you reduce a ball, it will just remove the last one that was created. Each one has its own frequency, rotation speed. Works really well. Yeah, it works really well. So that would have been, yeah, don't worry about the GPT-4o there. It was one of the O3 Mini or O3 Mini High that generated this. It's actually already available. Should be able to share the link somehow. Yeah, what's my brain doing at the moment? I'll share the link in the page, in the chat. How much memory? This one's only 29. I don't know if every block will generate more memory, obviously. Yeah, so the physics and everything seem to be correct, but yeah, there's obviously a few improvements that we could be making. Let me know what you think. What would you improve? Well, the obvious thing is being able to move the blocks and everything, actually build something. Then there's also, we could make them snap to one another. That could be nice as well. We actually have that in future directions for this thing. somewhere. Yeah, if everything we do is eventually on this website. And what else we've got? Yeah, we had this Mayo mock. So this is when I move my mouse, it's simulating EMG. So essentially, indirectly, it's recording the EMG of my finger. Moving the mouse. It works as well using keyboard. Wait, this is local at the moment. I can actually deploy. I have to. Let's quickly deploy. So we add the most recent tools we made to the site. And then we have the Python script that actually checks the website. Let's run that. Should have this error log. We should have had, yeah, the Lego. Yes, it's now available on the site as well. Yeah, because before we were showing it on the local server. Oh, bang. Yeah, sound effects would be handy for this as well. What do you reckon? What do you reckon? It will eventually fall. So it's still running. Only 31 megabytes. Bang. Okay, what else? We were saying we have that yeah, Mayo mock. It's simulating EMG using your mouse. That's the stuff that we're working on. This one's probably ready to be deployed. I kind of like it. It's nice and simple. We have a similar something called Mayoscope. This one you actually have to click a button and you have more controls like auto scaling. Removing the grid, the time window. Yeah, a lot of stuff. Baseline noise. Edit a little bit. Baseline noise, flex intensity. Whoops. Yeah, flex intensity is when you hit the flex button. So you can do little ones that are within the noise potentially. So yeah, that one needs some description at the bottom of the page and we will deploy as well. But yeah, if you're watching this streams, all of it is available for you because you'll see the link in the chat. And what else we got? Yeah, this one will have to be redone. Simulations, we have EEG signals, 4 of them, like 4 channels, and cognitive metrics changing. So based on the EEG, we'll have the spectral analysis not showing anything, and yeah, we could redo this one right now. I'm not sure how much time this will make. Yeah, just simulating EEG data and doing cognitive analysis to actually meant to be an indication of which one's which. I think it's there we stuffed up the CSS for this. But yeah, we need another few sessions probably during next week that we will try and make this work. Yeah, we had a similar thing with sleep cycle simulation. And this one actually showing, so that one meant to show spectral analysis. This would be just the FFT. This one does the spectrogram, so it's whatever, three-dimensional. You have color encoding, time on the x-axis and frequency on the y-axis. And yes, we do have only 1, 2, 3, 4, 5 frequencies, and that's in the code just to, have it something simple. And it's actually cycling through a deep sleep can increase the speed of the simulation, then something funny happening. Yeah, so it's going through current stage awake and showing you what the raw EEG REM sleep and the spectrogram looks like. But yeah, double speed does something funny to the rendering of the waveform and the spectrogram. So it's not nice. Oh, you can skip stage, so deep sleep, awake, REM sleep, and it will actually change the waveform and the spectrogram. But yeah, I have to probably make it somehow clearer, make sure it's working correctly. Or obviously this one has only one channel, but you can already check it out. Let me know what you think, because we will be trying to improve it next week or so. Have this spectral wave is something basic, meant to show you. Oh, it's white text, not nice. Meant to show you which microphone is being used. So currently I have two. Well, yeah, so in this case you can just see what difference it makes selecting a different microphone. So this one has this type of range when I speak. The other one should have a different range, but you can barely see it. I think this should be a difference on the noise it's picking up. If there's like a hum in the room, then you will see a clearer difference between them. Yeah, I think it's just quiet in the room, so you don't see it. The frequency is being added up, so if you have multiple microphones, it will just add up the energy in each frequency band that's being monitored. So that's another thing that, yeah, we might just keep it simple like that and publish it next week. I mean, it's already deployed and up and running. When I say publish, we will have a link to it on the landing page. it's really testing how they, work over a longer periods of time. Yeah, we have all sorts of other things for fun. Someone was actually asking if we're doing anything for fun. Well, yeah, we're doing a lot of games. And ooh, there's something wrong. Yeah, lots of games. There's a simulations, a spelling game. It's not meant to be in the correct order already. And this one actually has a complicated list of, so if you at the level, there's like 10 levels. And once you get to 10th level, there's this crazy medical term words that you have to, put in order. A device sense actually works, but you need sensors for it. I don't have sensors connected to this machine, so you can actually try it on your phone. It's pretty basic. And we're making some chat spots as well. Yeah, we're ready to deploy this one as well. Again, the games are really good for checking what the AI robots, LLM code generating bots can do. And yeah, the more I use it, the more I realize how amazing what they can do is. There's some Big Bang simulation. Sure if we should be jumping into any one in particular.
Music generation using AI ML involves various algorithms that can create melodies, harmonies, and full compositions. These algorithms can be broadly categorized into the following types. 1. Generative models. These models learn patterns in existing music data and generate new compositions based on learned styles. Recurrent neural networks, RNNs, used for sequential data like melodies and chord progressions. Example, long short-term memory, LSTM networks, which are an advanced form of RNNs that can handle longer dependencies in music sequences. Transformer models. These attention-based models have revolutionized music generation. Example, Music Transformer by Google Magenta can generate long and coherent musical sequences. Variational autoencoders, VAEs, used for latent space interpolation to generate novel melodies and harmonies. Example, MuseNet by OpenAI can generate complex multi-instrument compositions. Generative adversarial networks, GANs, useful for generating unique musical compositions. Example, GANSynth by Google Magenta generates realistic instrument sounds. 2. Rule-based and symbolic AI approaches. Markov chains. These probabilistic models predict the next note based on the previous ones. Grammar-based models use predefined rules and structures to generate compositions. Constraint-based systems ensure musical coherence by applying predefined constraints. 3. Hybrid models. Deep reinforcement learning, RL, used in interactive music generation where an AI agent learns to optimize compositions based on rewards. Example, Deep Jazz, an LSTM-based RL system for jazz improvisation. Symbolic AI plus deep learning. Some models combine rule-based composition with deep learning for more structured creativity. 4. Audio-based generation. These methods work directly with raw audio waveforms instead of symbolic music representations, MIDI. WaveNet by DeepMind uses convolutional neural networks to generate realistic audio. DDSP, Differentiable Digital Signal Processing by Google Magenta, merges deep learning with traditional DSP techniques for high-quality sound synthesis. 5. Evolutionary algorithms and genetic algorithms. Neat neuroevolution of augmenting topologies evolves neural networks for composing melodies. Genetic algorithms generate music by simulating evolution, selecting the best musical offspring. 6. Text-to-music and diffusion models. Stable audio by Stability AI and Refusion use diffusion models to generate music from text prompts. Music Gen by Meta generates music conditioned on text descriptions. Each of these algorithms has its strengths, and modern AI music systems often combine multiple approaches for better results. Do you have a specific type of music generation in mind, e.g., melody creation, full orchestration, or AI improvisation? Here's a detailed expansion of your idea. Vanilla HTML, CSS, JS, and JSON-based music generator with instrument selection, graph visualization, and GAN integration. Overview. This project is a browser-based music generator built using vanilla HTML, CSS, JavaScript, and JSON. It incorporates an instrument selection feature, interactive graph visualizations, and a generative adversarial network GAN for enhanced music generation. The system also provides user controls for customization and incorporates a hybrid model approach to refine the musical output. Core features. Music generation. Utilizes algorithmic composition techniques to generate melodies, harmonies, and rhythms. Implements JSON-based music storage for saving and retrieving compositions. Optionally integrates GANs for enhanced generative capabilities. Instrument selection. Users can choose different instruments, e.g. piano, guitar, violin, synth. Uses Web Audio API to synthesize or play sounds based on MIDI data. Allows real-time switching of instrument timbres. Graph visualization. Displays waveform and frequency spectrum using Canvas API and D3.js. Represents music structures, notes, beats, harmony progressions in a graph format. Provides interactive visual feedback on generated music. Generative Adversarial Network, GAN integration, implements a GAN-based AI model for improved melody generation. Trains a generator to create music and a discriminator to assess quality. Adapts based on user feedback, improving musical coherence. User controls, play, pause, stop, loop options. Tempo and key signature adjustment Instrument and sound effects customization, MIDI export for external music software. Hybrid model approach combines rule-based composition, traditional music theory, with GAN-based learning. Uses a weighted hybrid algorithm for balancing AI-generated and user-guided composition. Supports style transfer, e.g. classical, jazz, EDM. Technology stack, HTML5, structure and UI, CSS3, styling and animations, JavaScript E6 plus core logic, web audio API, sound synthesis and playback, D3.js Canvas API, graphical representations, JSON, data storage for music structures, GAN model, Python JS backend, AI-based composition. Use cases, music composition and experimentation, educational tool for learning AI and music theory, interactive visualization of music data. Would you like a sample code structure or further details on implementation? No, you don't necessarily need a backend for a vanilla HTML, CSS, and JavaScript music generator. You can build the entire system as a front-end only client-side application using JavaScript, the Web Audio API, and JSON for data storage. However, a backend might be required for certain advanced features. Here's a breakdown. No backend required, pure front-end approach. If you want to keep everything lightweight and in browser, you can avoid a backend by leveraging Web Audio API for sound synthesis and playback, local storage IndexedDB for saving user preferences and compositions, JSON files, preloaded or dynamically generated for storing music patterns and AI-generated content, web workers to offload intensive calculations like GAN processing, though limited in scope. Limitations without a backend. AI-based music generation GANs would be tricky since training a deep learning model in JavaScript is computationally expensive. File storage would be limited to client-side storage, e.g. local storage, IndexedDB. Sharing and collaboration wouldn't be seamless without a cloud-based storage solution. Backend required, hybrid approach. If you want AI-powered generation, cloud storage, or real-time collaboration, a backend will be useful. A backend would handle AI model processing, GAN-based music generation via TensorFlow PyTorch, MIDI file storage and retrieval for user-generated compositions, user authentication for saving personalized settings, collaborative features, e.g. real-time composition sharing, tech stack for backend if needed, Node.js plus Express, lightweight API for handling requests, Python, Flask Fast API, or TensorFlow.js for AI-powered music generation, Firebase/Supabase for easy cloud storage and authentication, PostgreSQL MongoDB for structured music data storage. Best of both worlds? You could start with a front-end only version and later integrate a back-end only for AI processing or storage, making it a hybrid system. Would you like a front-end only prototype, or do you need AI-powered features from the start? Here's a more detailed breakdown of your project. Vanilla HTML, CSS, JS, and JSON-based music generator, a web-based music generator that uses a hybrid model combining rule-based composition with deep learning to create music. The application will feature instrument selection, graph visualization, user controls, and an interface for generating music based on music theory principles such as chord progressions, melody generation, rhythm, and harmony. The deep learning model will be trained in Python and then deployed in the front end using JavaScript. Project features: 1. User interface, HTML, CSS, JS. A simple vanilla JavaScript front end with no backend. UI components, instrument selection, drop-downs or buttons for choosing different instruments. Graph visualization, a real-time graph representation of generated melodies, chord structures, and rhythm. User controls, button sliders for adjusting tempo, key, scale, and other parameters. Music generation model, a hybrid approach, rule-based composition, implements music theory rules for creating chord progressions, melodies, harmonies, and rhythms. Generative Adversarial Network, GAN, a deep learning-based approach trained in Python to generate music patterns. The model will be trained in Python and exported as a lightweight format, e.g. JSON or TensorFlow.js model, to be used in JavaScript. 3. Instrument selection. Users can choose between various instruments, e.g. piano, guitar, violin. Different sound samples or MIDI synths will be available for playback. 4. Graph visualization. A real-time graph visualization for chord progression, nodes representing chords connected based on harmonic relationships. Melody generation, a timeline-based pitch visualization. A percussive beat representation. 5. User controls, adjustable parameters, tempo, BPM, key signature, scale selection, major, minor, etc., instrument settings, playback options, play, pause, stop music, export generated music as MIDI or JSON. Implementation steps. 1. Train the deep learning model Python. Use GANs for music generation. Train on existing MIDI datasets. Convert trained data into a JavaScript-compatible format, e.g. JSON or TensorFlow.js. 2. Develop the web interface, HTML, CSS, JS. Build a clean UI with instrument selection, user controls, and visualizations. 3. Implement the music generation algorithm, JS. Load the trained model into JavaScript. Combine rule-based logic with AI-generated sequences. 4. Add graph visualizations. Use D3.js or P5.js to create real-time music representations. 5. Testing and deployment. Ensure smooth user interaction. Optimize for performance and real-time playback. Would you like code snippets for specific parts like music generation, instrument selection, or visualization? Music Generator Web Application. Shasht Overview. This document provides detailed instructions for a developer to implement a music generator web application. The application will allow users to select an instrument, generate music using a generative adversarial network, GAN, visualize the music, and listen to the generated composition. The application must run entirely in the browser without requiring a back-end server. The GAN model will be trained using Python and deployed using JavaScript. Here are a few details you might consider adding, depending on the project's complexity and the developer's familiarity with the technologies. 1. Node.js environment. Node.js version indicate a recommended version, e.g. 16 plus or 18 plus, and any specific NPM dependencies needed for TensorFlow.js or other libraries. Package management. Any notes on using NPM or Yarn, plus a package.json file with exact versions of libraries like at TensorFlow/TFJS, Tone, etc. 2. Local development server setup. Explain whether a local development server, e.g. live server, HTTP server, or a React-based setup is needed for testing the front-end locally. Mention if any CORS or HTTPS constraints might affect TensorFlow.js model loading. 3. Data augmentation, optional. If the training process benefits from pitch shifting, time stretching, or other forms of data augmentation, describe the recommended approach or scripts. 4. MIDI file handling. Additional details on how to structure the MIDI dataset, e.g. consistent tempo, key normalization, before feeding it into the preprocessing scripts. How to handle multiple instruments within a single MIDI file, e.g. focusing on specific tracks or channels. 5. Version control and continuous integration. Suggest a recommended structure for commits, testing, or even a CI pipeline to ensure the Python training scripts and JavaScript model loading both work in tandem. 6. Docker or virtual environment setup, if relevant. If the team uses Docker, provide a basic Docker file or instructions for building an image that includes all necessary dependencies. If a virtual environment, e.g. Venv, Conda is standard, list any best practices for installation. 7. Debugging tips. Python and JS, recommendations on how to troubleshoot training issues, e.g. checking TensorBoard logs, verifying model weights. Advice on debugging TensorFlow.js in the browser, using the browser console to monitor CPU, GPU usage, or capturing any error messages. 8. Performance benchmarks. If performance is a concern, briefly outline how to measure and optimize both the training, e.g. how many steps second, and browser inference times, e.g. how quickly the model generates audio on typical consumer hardware. Including these points can save time for the developer, reduce guesswork, and ensure a smoother workflow from data preprocessing all the way to web deployment. Here is the updated document with all the suggested additions regarding data augmentation, basic error checking, and performance considerations for quick inference. Let me know if you need any more changes. Yes, the instructions are very clear. They provide a detailed overview of the project's features, the technology stack for both the front-end and back-end training components, as well as a well-organized file structure. The step-by-step breakdown from UI development with HTML, CSS, JavaScript, and model inference using TensorFlow.js to audio playback with Tone.js and model training in Python is comprehensive. A couple of points for clarification or further consideration. While basic error checking is mentioned, it might be useful to specify more detailed error logging or fallback mechanisms for things like model loading failures. Performance optimization. The instructions mention optimizing model size and inference speed. We might need additional benchmarks or target metrics to measure success. Browser compatibility. Although not explicitly stated, it could be helpful to define browser compatibility requirements, especially regarding WebGL and audio APIs. Overall, I'm confident with these instructions and ready to move forward. Let me know if you want me to start coding or if you need any adjustments. Here's a concise summary of the project along with some potential issues to consider. Project summary. Backend Python, enhanced GAN architecture, generator. Uses dense layers followed by LSTM layers to produce a piano roll style sequence, 32 time steps, climbs 88 notes. Discriminator. Uses LSTM layers with dropout to evaluate these sequences. Data preprocessing uses Pretty MIDI to convert MIDI files into piano rolls. Segments these piano rolls into fixed length sequences, e.g., 32 time steps, and normalizes note velocities. Implements a standard GAN training loop where the discriminator and generator are trained adversarially. Logs average losses per epoch and saves the trained generator. Model export. Converts the saved generator model into TensorFlow.js format for front-end use. Front-end, JavaScript, HTML, CSS, user interface, provides an HTML page with instrument selection, parameter sliders, generate play buttons, and a canvas for visualization. Model inference. Uses TensorFlow.js to load the exported model and generate a musical sequence from random noise. The output is reshaped into a 2D piano roll array, 32 time steps, 88 notes. Visualization. Renders the piano roll on a canvas where each cell corresponds to a note at a particular time step. Playback. Uses Tone.js to play back the generated sequence. Note. The current playback function was originally designed for a sequence of note objects and may need adjustment to work with the 2D piano roll format. Potential issues. 1. Playback function mismatch. Issue. The playback code expects note objects with properties like note, time, and velocity, but the enhanced now outputs a 2D piano roll array. Solution. Update the playback function to extract note on-off events, or translate the piano roll data into a sequence of note events, e.g. by scanning each time step for notes with velocities above a threshold. 2. File paths and model export consistency. Issue. The export script saves the model in /frontend/trained model, yet the frontend code attempts to load trained model.json. Solution. Verify and adjust the file name's path so that the exported model is correctly located and named for TensorFlow.js to load it. 3. Assumptions on model output shape. Issue. The reshaping logic in Generate Music assumes a fixed output shape of 13288. Any modifications to the generator's architecture or output dimensions would require corresponding changes in the reshaping code. Solution. Ensure the model architecture and the output processing remain in sync, or add dynamic checks to handle different output shapes. 4. Dataset file path. Issue. The training script expects the preprocessed data file, processdata.pkl, in the current directory. Solution. Make sure that the file paths in preprocess.py and train.py are consistent and adjust them as needed based on your directory structure. 5. Error handling and logging. While basic error handling is included, e.g. try-catch blocks, additional logging might be necessary, especially for asynchronous model loading in the browser and during training. Solution. Enhance error handling and logging for better debugging and production readiness. 6. Browser compatibility and performance. Issue. Depending on the size of the model and the complexity of real-time visualization, performance might vary across consumer devices. Solution. Consider performance optimizations such as model quantization, efficient canvas drawing techniques, and fallbacks for devices with limited capabilities. This summary and these points should help ensure that you're aware of both the overall structure and any adjustments you might need as you continue development. Let me know if you'd like to dive deeper into any specific area. Below is an updated version of the original instructions that addresses the issues identified during development. Music Generator Web Application Development Instructions. Overview. This document provides detailed instructions for implementing a music generator web application. The application will allow users to select an instrument, generate music using a generative adversarial network, GAN, visualize the music, and listen to the generated composition. The The Music Generator web application is a browser-based tool that allows users to create AI-generated music using a generative adversarial network, GAN. The application provides an intuitive user interface where users can select an instrument from a predefined list, adjust parameters to influence the music generation process, visualize the generated composition, and listen to the output using an integrated playback engine. It is designed to run entirely in the browser without requiring a backend server, making use of JavaScript libraries such as TensorFlow.js for model inference, Tone.js for sound synthesis, and the Web Audio API for audio processing. The front end of the application consists of an HTML-based interface styled with CSS to ensure a user-friendly experience. It includes drop-down menus for instrument selection, sliders for adjusting generation parameters, a button to generate music, and another to play the output. The visualization component dynamically renders the generated composition as a piano roll or MIDI-like notation using the Canvas API, enabling real-time updates synchronized with playback. JavaScript manages user interactions, model inference, and data processing, ensuring smooth transitions and error handling through asynchronous operations. The backend model is trained using Python and designed to generate structured musical sequences in the form of a piano roll, which is a time step-based matrix where each column represents a specific time frame and each row represents a musical note, with values indicating the note's velocity or intensity. The model consists of a deep learning GAN, where the generator learns to create realistic note sequences while the discriminator evaluates their quality. The training data consists of MIDI files that are pre-processed using the Pretty MIDI library to extract melody, harmony, and rhythm information. This data is then segmented into fixed-length sequences to ensure consistency in training. The training process involves iterative optimization, where the generator progressively improves at producing sequences that resemble real musical patterns, while the discriminator refines its ability to distinguish between real and synthetic music. Once trained, the generator model is exported to a TensorFlow.js compatible format and integrated into the front end for real-time inference. When the user initiates music generation, the front-end code loads the model, applies the selected instrument and parameter adjustments, and generates a sequence based on the trained model's output. Since the GAN model produces a structured sequence, additional processing is required to interpret the data for visualization and playback. The piano roll output is reshaped into an array format suitable for rendering on the canvas, where active notes are visually represented as colored bars or dots, with their opacity or intensity reflecting the note velocity. Playback is handled using tone.js, which converts the generated piano roll into a series of MIDI note events. These events are scheduled in real time, ensuring that the timing and duration of each note align with the intended musical structure. The Web Audio API is utilized for low-level sound synthesis, allowing for additional effects such as reverb and equalization. Since the original playback function was designed for simple note sequences rather than a full piano roll, modifications have been made to detect active notes in each time step and schedule them accordingly to achieve accurate sound reproduction. The application includes several optimization strategies to enhance performance and usability. Model size is minimized to ensure fast loading times, and inference is optimized for execution within the browser using WebGL acceleration when available. The visualization is designed to be lightweight and responsive, ensuring smooth animations across different devices. Additional error handling mechanisms are implemented throughout the code to detect and log potential issues, such as missing files, model loading failures, or incorrect user inputs. The project also includes comprehensive testing across multiple browsers to ensure compatibility and reliability. Data preprocessing plays a crucial role in improving the quality of generated music. The dataset consists of MIDI files covering a wide range of musical styles and instruments, which are carefully curated to provide a diverse training set. To enhance generalization, various data augmentation techniques are applied, including pitch shifting to transpose melodies to different keys, time stretching to modify note durations, and instrument variation to ensure adaptability across different sound sources. The pre-processing pipeline ensures that all MIDI files are standardized, with consistent tempo adjustments and key normalization to maintain uniformity in training. The training process follows a structured approach with defined hyperparameters to balance learning efficiency and output quality. Batch sizes, learning rates, and optimization strategies are carefully chosen based on available hardware capabilities. The training loop continuously evaluates the generator's output against real samples, adjusting weights through backpropagation to refine the model's ability to create coherent and expressive music. Metrics such as loss values and accuracy scores are monitored throughout the process to detect potential overfitting or underperformance. Deployment of the application is streamlined to ensure seamless user interaction. The trained model is packaged within the front-end directory, eliminating the need for external API calls. The interface is designed for ease of use, with intuitive controls and minimal latency between generation, visualization, and playback. Future enhancements could include additional customization features such as tempo adjustments, dynamic instrument selection, and expanded sound synthesis capabilities. Further optimizations may involve implementing model quantization to reduce computational overhead and exploring reinforcement learning techniques to improve the adaptability of generated compositions. Overall, the Music Generator web application integrates deep learning and interactive web technologies to provide a fully functional in-browser AI music composition tool. With an efficient GAN-based model, a robust data processing pipeline, and a carefully optimized front end, the application enables real-time music creation while ensuring a smooth and engaging user experience. Through continuous refinement and feature expansion, it has the potential to evolve into a powerful platform for AI-assisted musical creativity.